Welcome to the APL quest. See APL Wiki for details. Today's quest is the fifth problem from the 2014 round of the APL problem solving competition. It's a pretty simple problem. We just to find out whether a given text is a palindrome. Slight complication is that we need to make sure to ignore things like case and punctuation. Let's start with some test data. Okay, so we need to get rid of case differences, so that, for example, the first A and the last A in Panama match each other. And we can use quad C, which is case fold, for that. Now, we just need to sort out the characters that we need to compare and get rid of those that we don't want to look at all. And one way we can do this is let's put this into a function so we can try this. This is the case folded one, and then we should look which characters are members of the case folded alphabet. Oops. Yeah, of course it should be omega here. There we go. Okay. And then we can filter by that Boolean vector. Let's call this just the letters. And the last step is to see if the letters match themselves when they are reversed. We can see that a man, a plan, and so on is a palindrome, whereas hello world is not. This works, but we can do it a little bit more elegantly by making some observations about what we've got here. Firstly, filtering by membership is the same thing as intersection. So we can actually substitute this whole thing in and say the intersection between the case folded argument and the case folded alphabet. Notice that we are applying intersection after pre-processing both arguments with case folding. This calls for an over. Finally, we are comparing this L to its reverse. An operation between the identity of some value and some pre-processed value, we could call that a hook construct. But really what is another way to think about it is that we are applying the match function between L and L on itself. So that means we're doing a selfie, only that before we apply match, we pre-process the right argument of match with reverse. And then, since we're only using this variable once, there's really no point in assigning it. So we can just put it in line. There's also a possibility of making this a fully tacit function. It's quite simple here because we just have a dyadic function applied between the argument and a constant. And then we apply another function monadically on that. So clearly this whole thing is an atop. One thing applied and another thing applied. Only that we have here a dyadic function where the one argument is constant. So we can bind the alphabet as a constant right argument to it. And that gives us a very neat tacit solution. Let's call this A. It does have, however, a little bit of a performance issue, namely that we are case folding a potentially very large argument. All we need to do is we want to see to only keep those characters which are uppercase and lowercase letters. And the whole reason we're case folding the whole argument is just so that we can take the intersection with the letters. Now, the input might be of an unknown size, but the alphabet is of a known size. And so we can optimize this a little bit by simply keeping the intersection, but instead of case folding both arguments, we only case fold the alphabet. Now, this is a problem, of course, because this only gives us lowercase letters, and we might also have uppercase letters. So let's just supply the uppercase letters as well. This is a one-time operation when we define the function, generating an uppercase and lowercase alphabet, and then we just do the intersection on that. So that saves us from doing the case folding on the entire argument, and that might speed up things a little bit. So these are the basic solutions, but we could actually go a whole different route, and that is to compare ranges. So instead of looking for intersection, which is a set function, we can look at where in the Unicode character set do the characters fall. Because all the, in Unicode and in ASCII, all the uppercase letters are contiguous and all the lowercase letters are also contiguous. And so if we look at the values for the beginning of the uppercase alphabet, the end of the uppercase alphabet, and also the beginning of the lowercase alphabet and the end of the lowercase alphabet. Oops, sorry, we need an each there. Okay, so we can see from 65 to 90, from 97 to 122. Now, interval index, which is what we're going to use for looking up ranges, it is inclusive on the left, on the beginning, and exclusive on the end. So we need to go one up at the end, and then we can look at what those characters are. So this is these are the characters that we want to use for cutoffs. And so we can see that some characters fall inside this interval here. That's number 1 between these two. And then 0 is before the first one. And then some fall over here. And then there might also be some that fall, some punctuation that falls here, but that's pretty rare. Which means that it's every other interval which we want. If it's 0, it's outside, we don't want it. If it's 1, it's an uppercase letter. If it's 2, it's lowercase. If it's some punctuation, and if it's 3, it's lowercase. I mean, if it's 4, then it's beyond the lowercase and it's more punctuation that we don't want. So we can take the division remainder when dividing by 2, and that gives us a 1 for all the odd ones, so which is exactly where we have uppercase and lowercase letters. And that is what we need to use to filter with. So that's another way of doing the filtering, and then we can apply the actual palindromic testing as we've done before. Oops. Oh, we've of course been missing the case folding once we're done with that. There we go. Let's call the C. Actually, we can make this one test it as well. Before we give it a name, let's just try that. So there's an interesting problem here with the slash, which is a hybrid operator function. We can begin by fixing that with a top, and then we have a dyadic function with a constant left argument, so we can just bind that over here. And then we have the argument over here, case folding, and then comparison. So we could write all of it like this. See? But since we are anyway post-processing the result from the replicate or compress here, then we don't actually need to use an identity function to do with the top to force it to be a function. We could take this whole thing and move it in here as well. So let's call this C. But this whole business of case folding, and that means that we need to consider every character whether or not it needs to be case folded. That is potentially expensive, and if we can operate on raw code points, we might get a significant performance advantage. Now, how is that going to work? So, if we start immediately by converting all the characters to code points, if they are all ASCII, then that's really cheap because that means we can because the code points are essentially unsigned byte values, unsigned integers. If there are some characters that are outside of ASCII, then we'll end up having in values larger than 127, and we'll have to go to 2-byte integers because the integers internally are signed, but still it's going to be pretty cheap operation to switch to code points like this. And then we need to check whether they are in this range that we used before, and we can write this in a tacit way that I really like for ranges. So there are two ranges we're looking at, and we want to know if it's in either of those ranges. And so the way we can, APL doesn't allow you to write x or something like a is less than x is less than b, because less than is just a function and it would bind wrong. But we can write that 65 is less than or equal to, and the value is also less than or equal to 90, so that's the upper bound. And this kind of reads nicely, right? 65 is less than or equal to, and it's less than or equal to 90. So that's the uppercase. And then lowercase is 97 is less than or equal to, and it's less than or equal to 122. So this, I like writing ranges in APL like this. So this again gives us the elements that we are interested in. And then we need to use that to filter, but we're not filtering the characters now. We are filtering, because then we need to case fold. We're filtering the code points. So we give this a name, u, and then we'll filter u with that. And that gives us all these values. Now, it might not be easy to see what's going on here, but if we just temporarily apply quad UCS to it, we can, oh, we should do it each again. Then we can see our letters that we're interested in. Now, here's the thing. ASCII, and then by extension Unicode, because it's just a superset, is constructed in such a way that there's a single bit difference between uppercase and lowercase. And that's that means that we can do a division remainder with 32. And that is, since we're not, it doesn't matter that there are many other values that would collapse to the same division remainder with 32, because we only look at uppercase and lowercase letters. So the only thing we need to know is like the offset from the beginning of the alphabet, and 32 gives us exactly that. Now these aren't useful byte values, but we're not interested in byte values. We're just interested in these, should we say, labels on the characters, and see if they are the same. And then we can check using the exact same thing as before whether or not we've got palindrome. So by working on code points, the code is significantly more involved, but we might potentially avoid some expensive operations there. Okay, let's have a look at the performance. We're copying a CMPX from defense. And then we're going to, we need to create some test data, of course. So let's create some test data. Say we overtake from the uppercase and the lowercase alphabet, much like we did with the uppercase lowercase alphabet before, followed by a little bit of punctuation that might happen there. So because this adds up to much less than 70, that means we'll get some spaces as well. So it kind of looks like natural text. And there are obviously 70 here, and let's just do 50 of them for now, just to see what this looks like. So this kind of looks like natural text with a little bit of punctuation there. It's not really very important. And so this is a case. So let's put it over here. 1E5 should be enough. And then, so this obviously isn't a palindrome, but we can create one that is a palindrome, and we can do that simply by let's take half of this. So this is 5E4, and then we can just so it's the same kind of construct. The hook construct. We are self-concatenating it, and then we are reversing it, and before we concatenate one of them. So this concatenated to its reverse could be read as concatenated to its reverse. This is obviously a palindrome. And now we can say CMPX on A, B, C, and D, each one of them with the entire argument of T. So this is on a non-palindromic case. And we can see that our solution where we avoid case folding the input instead having a both uppercase and lowercase alphabet for the intersection, that did save us significantly. Doing the intervals with raw characters, that's not worth it. However, switching to code points gives us a significant speed up in this case. And we can, just for good measure, we can try this with the palindrome as well. We'll probably see similar results. Yeah, that looks very much the same. So that's all for checking for palindromes. Thank you for watching.